A recall or a recap of what we have dealt with so far with regard to Ohm's law. Um, so this was an experiment that was conducted by George Simon Ohm in the second half of the 18th century. His basic question was, how does the current and the potential difference vary in a circuit when you use different lengths of some conductor? He proceeded to set up the experiment in this manner, and all of this is recall. Okay, I'm just recapping whatever we have done so far. Switch and um, a variable resistor. So that's another new term that I'm introducing. A variable resistor is just a name given to a resistor, which has a possibility but for varying the length of the resistor. So you use a movable jockey, just a crocodile clip that can clip onto different parts of the wire, and depending upon how much length of wire you use, you are able to change the voltage and therefore the current in the circuit. I'll just put an ammeter over there. So the way you do that is, of course, you use a voltmeter and an ammeter. You connect the voltmeter across the circuit like that. Mind you, this resistor is not touching this wire. Okay, then it might not work. So like somebody pointed out yesterday, you're measuring the potential difference between this point and this point in the circuit. So by collating a set of values for the voltage and ammeter by changing the length of the wire, you're going to get values for it, for voltage and current for various lengths of the wire. And when sorry, I want to change the color of that. And when you plot the graph of current versus voltage, and I just had a discussion with somebody else about why do you put current over here and why do you put voltage over here? And the reason that I was told, I was reminded, actually I knew about this but I had kind of forgotten about it, is that when you plot a graph, you put the value of what you are changing over here, and you put the dependent value that is being changed on the y-axis. So what you know you are changing goes on the x-axis, and the dependent value goes on the y-axis. So that is why George Simon Ohm put it in this manner. And of course, when the points were plotted, we find that there is a sort of linear graph that comes out with the various readings falling almost on a straight line. Of course, when you're doing the experiment, these dots will not exactly fall on the straight line. They'll be a little bit up and down, but the best fit curve will be that. The relevance of this is that the voltage and current are proportionally increasing with one another. So when you change a certain amount of voltage, a certain amount of current always changes. And that will give you the relationship when you look at the slope of the graph. It will give you I upon V, which will be a constant. Okay, and that constant, of course, was nothing but 1 upon R. Okay, and this relationship gives you Ohm's law. That is, to rearrange the equation, you get V equals I times R. Okay, and the voltage is the measured potential difference across a circuit. The current is the I is the current in the circuit, and R is the resistance. The voltage will be measured in volts. The current will be measured in amps or milliamps, and the resistance will be measured in a unit, which was named in the honor of George Simon Ohm. So that was another honor that was given to him. I don't think it was in his lifetime, but it was named after him. The unit for resistance was given his name. And therefore, we come to this new quantity. We know what is potential difference. We know what is electric potential at a point. We know what is current. And now we understand what is resistance. Okay, so resistance is basically the quality of a material to resist or allow the flow of current in a circuit. Okay, so when there is more resistance, there is more potential drop across the circuit, and therefore there is lesser current flowing through the circuit. If the resistance is low, then the current flow is more. So resistance has that relationship with current and voltage. Resistance is measured in ohms, uh, OHM, ohms, and its symbol is the capital omega. Okay, that is from the Greek symbol. So the symbol is given in ohms. You have a resistance of 1 ohm, and then you can have a resistance of 1000 ohms, which will then be called kilo ohms, and 1000 kilo ohms will then make what, 1 mega ohm, am I right? And so on and so forth. It follows the same principles that we have seen in terms of uh, units and their multiples earlier. Any questions or doubts so far before we move into the next part? Just give you a few seconds to do that. All right then. So if all that is clear, what we have done so far, so these graphs and these diagrams, we have seen it several times. So I'm just going to get rid of all that. I'm just going to keep the resistance and so on over there, and then move into talking about resistance. So how do we sort of imagine the resistance within a wire? So the textbook puts it in certain ways, and we'll sort of have a discussion about that and try to understand. So what does the resistance of the wire depend upon? Maybe what I'll do is I'll put down 2 or 3 factors. Okay, factors affecting R. And you people tell me, these factors do matter, but you people tell me, how do you think these factors affect the resistance of any given conductor? I hope that point is clear. First factor that I'll put down is length. Okay, so when I talk in terms of length, George-Simon's own experiment has adequately demonstrated that if you take a wire of the same dimensions, which means the cross section of the wire does not change. Okay, so any wire has a certain cross section, a width over here. Okay, and if you take 2 wires, one which has a length L and another which has a length L by 2, and let's say the resistance of this one is R1 and this one is R2. I hope all this is clear what I'm trying to say. Okay, which do you think will have greater resistance? So you can message me the answer, which will have greater resistance, R1 or R2?
R1.
Okay, and those who don't want to talk can send it by message. Yeah, okay. People are saying R1. Some of them are saying longer wire. R1, longer wire. Okay, okay. All right. So it's obvious from the experiment that we just discussed that R1 is going to be greater than R2. So R1 is going to be greater than R2. So what is the effect of length on the resistance of a conductor? If you can just kind of put it as a statement.
Length is proportional to the resistance.
Yeah, length is proportional to resistance. They are directly proportional, correct. So if you have more length, there will be more resistance. Okay, so as long as the diameter of the wire, as long as the dimensions of the wire are kept uniform, there is no question about it. When you have greater length, you are going to have greater resistance. So that's fine. Let's look at a second factor. In fact, there is another factor which we could have looked at before. Let me just include that then. Material. Okay, so let's say that you have two materials. One of them is copper. Okay, um, comparing materials. So you have copper, and the other material is, let us say, what can we say? Give me something. Not very close, but something that we can compare with.
Nickel?
Sorry,
Nickel?
I couldn't hear that very clearly. There seems to.
Nickel.
Pardon?
Nickel.
Nickel. Okay, let me put as tungsten because I think that will be a clear thing. Okay, both are sort of elemental metals, Cu and tungsten W. Okay, we have already discussed this, so it's not a mystery. Which of these two materials, for the same length and same dimensions, will have greater resistance? Let's say that this is the resistance of copper and this is the resistance of tungsten. So which will be greater?
Tungsten.
Yeah, but why do you say that? Any particular reason why you're saying tungsten will be greater?
Nothing much.
It's
Anybody
used
else?
in bulbs as bulb filaments, right?
Yeah, it's used in bulbs as bulb filament. And so why are you saying it has greater resistance?
Because like when the current passes through it, it lights up because of the resistance, and that's why the bulb works.
Yeah, exactly. So you know from before that a tungsten filament actually heats up and converts the energy. And it must be converting the energy and getting heated up only because it has greater resistance. I mean, presumably because it has greater resistance. Okay. So therefore, it's a matter of knowledge that we say that therefore the resistance of tungsten must be higher, in fact, way higher than the resistance of copper. And because we use copper in circuits for making connections and so on, we know that copper must be having very, very low resistance. Otherwise, circuits will get heated up if copper has high resistance. So material is another very important factor that affects the resistance of any given object. Okay, so we have taken care of those two factors. In fact, I should have first talked about material and then about length. So that brings us to the third thing. Let us say you have two resistors of the same material, okay, but and also the same length, but one of them has half the surface area, cross section, I mean, not surface area. So I'm looking at the cross section. So this surface area and this surface area. So this is A and this is A upon 2. So now if I say that the resistance of this is resistance 1 and this is the resistance of this is resistance 2, which do you think will have greater resistance? And this is like a little bit informed guesswork. So you can tell me. You can message me also. And we'll try to discuss like why do we think either this or that has greater resistance. Any takers? Any guesses?
I think it'll be inversely proportional to area.
So you can just tell me in terms of R1 and R2.
I'm guessing R1 would have, R2 would have 4 times the resistance.
Okay. So you're using the word 4 times. Okay. But basically you can say that R2 is greater than R1 And what would be your sort of general idea of why that is true? Why will the thinner wire have, so to say, a thinner wire will have greater resistance than the thicker wire?
I'm guessing that resistance happens because of free electrons, because in superconductors, which are very cold, it doesn't. So I'm guessing it's because of free electrons. So if the area is larger, the
More material is available, and the more material that is available, this is usually we are talking about metals, and metals have free electrons in their lattices. So if you have a larger surface area, there are more free electrons, and those free electrons are then responsible or helpful in terms of moving the current across. Can we put it like that?
yeah, yes.
Yeah. So okay. So that is a very general understanding of it, and I'm not 100% sure that it is actually a correct sort of way of understanding it. But it's all right. The textbook kind of puts it like that. That what happens is, in terms of flow of electricity, we need free electrons, and I guess you have studied this in chemistry, that metallic lattices, there are atoms which are bound to one another by metallic bonds, and that there are these free electrons, the concept of free electrons, which are electrons which are unbounded to that particular copper atom, let's say, if we are considering copper now. So therefore, in a conductor with larger surface area, there are more free electrons to participate in the process of moving electricity. Okay, whereas in a conductor with a smaller surface area, there would be lesser free electrons. So because there are more free electrons to help move electricity along, the resistance of a larger surface area or larger cross section area of the wire is going to have lesser resistance. So that is the reason why a wire with a larger cross section will have lesser resistance than a wire with smaller cross section. And you can also see this in terms of household devices also. So if you open up a toy or something like that, you will find inside that there are very thin wires which are used for making the connections. You can, or even a torch battery, a torch, if you open up also, you will find similar things. But if you go for larger appliances, like say for example an electric iron, or the geyser, or your microwave, refrigerator, there you will find that the wires are thicker. So if you want a larger current to go across, because these are big larger devices, so they need more electricity, more current, so therefore their wires would be made thicker. You cannot put a large amount of current through a small wire, because the wire would then heat up because of the higher resistance, and there is a fire accident that is possible. So that is why they use wires with larger cross section for devices which use greater amount of current. I hope I made that point clear. If there are any questions, you can ask about it. Hardik, you say larger area for the electrons to flow through. You can remember it like that, but you can't put it like that. Okay, you will have to talk in terms of free electron availability. A larger cross section means there is more copper or whatever metal we are talking about, and since there will be more atoms, there will be more free electrons, and therefore current, the resistance goes down. And finally, Ishan, you mentioned that the proportion will be a specific value, 2 times as much, 4 times as much. Sorry. So why did you say that?
No, I was squaring it because it's a circle or something. So
Yeah.
area is usually in meters squared, it doesn't square.
Yeah, yeah.
It's a by 2, so then it'll become four times that, right?
4 times that much, yeah. So that's another relationship that can be deduced from what we have seen so far. It's not strictly part of your syllabus, so you don't need to memorize that. It's there in your textbook, you can study it. But the relationship is not linear. So if I ask in terms of like compare R1 and R2, right? Then it's not that R1 is 2 times as much as R2. R1 will be 4 times as much as R2 because area is typically square. So for example, if you take a circular one, which is a little bit more difficult, the proportion of the area between these two will be pi r squared r1 square, let's say. This will be, let's say that the diameter of this is r2 and the diameter of this is r1. Okay, so the comparison will be r1 squared, pi r1 squared by pi r2 squared, and of course pi and pi will get cancelled out. Uh, if the radius of this is twice as much as r2, so you will get 2r2 whole square divided by r2 squared, right? So that will give you 4 by 1, a ratio of 4 by 1. All right. So because it's an area function, the ratio of the resistance is going to be 4:1. That means the resistance of this wire R1 is going to be 1/4 of the resistance of R2. So that's what it means. It's a relationship that you can think about. We will discuss this later. Right now, we don't need to labor it. Any questions about this? I just mentioned it because Ishan happened to have mentioned it. Okay. And finally, we have talked about material length and cross-section area. Finally, you can expect some questions, although they haven't asked it in the recent past a lot. If you take any length of a resistance, let's say a certain length of resistance L. Okay, and they say that this length has a resistance R1. Now, they could ask you a question, what will happen if you double this wire up on itself? I hope you are able to understand that. When you double the wire upon itself. Okay. Now, let's say that this has a new resistance R2. Can you tell what is the resistance of R2? Okay, of course, you have to give the values for R1 and the actual length for you to be able to answer that question. Actually, the length doesn't matter. You just need to know what is R1. So two things are happening over here. Okay, one is that the length has presumably halved. Okay, so that will have an effect on the resistance. But if you double the wire on itself, then the area of cross section also doubles. I mean, that looks like an 8, but what I mean to say is the area of cross section doubles, because here you have one cross section, right? And over here, since you have doubled it on itself, you have double the area. So they have asked questions like this in the past. What will be the effect on the effective resistance of this when you double the wire on itself? So you have to take into effect that the resistance will decrease because of the increase in the length, but the resistance is also going to decrease because of the doubling of the cross section. And you have to take both factors into account before answering that question. So if there are any questions that are there in the current exercise which deal with that, at that point of time, we will try to answer this question. Any comments upon this question, this type of question? Anybody would like to say something? Okay. So then finally to sort of talk in terms of external factors that affect the resistance of a circuit. There's just one minor point to discuss. I'm hoping there aren't any other questions regarding whatever I have discussed up to this point of time. If there are, please do raise it now. So, what kind of external factors affect the resistance of the circuit? So, external factors. So there is one external factor that we can discuss about, which is temperature. Okay, and what would your guess be if you have a conductor of a certain dimension, and the temperature, and it had a certain resistance at that temperature. If the temperature increased, what would happen to its resistance? So you have a certain conductor, conducting wire, with a certain cross section area made of a certain material, and it had a resistance R1 at temperature T1. Okay, if T1 increased, if T1 goes up, what will happen to the resistance? Any guesses? Think in terms of the availability of free electrons and what happens to free electrons when the temperature increases, if you can kind of guess it. Come on, we haven't got all day. Last point to be discussed before we stop.
The resistance would increase, right?
When temperature goes up, resistance will increase. And why do you say that?
Because the particles will be moving around more, so there will be more collisions.
Yeah. Again, that's one way in which you can visualize what is happening. I doubt if that is actually what is happening or that is the correct explanation. One thing is very clear: when you increase temperature, the resistance also increases. Okay, and that's a little counterintuitive, because we would think that if the temperature increases, it is more easy for electrons to flow through. But that is not the truth. What happens is that because the temperature increases, the atoms themselves increase their kinetic energy. Okay, so the vibrational, translational kinetic energy, so they vibrate more. So because the atoms vibrate more, and mind you, this is just a kind of picturization or visualization of what is happening, it may not entirely be true. The electrons that are flowing through, drift velocity, which are going through the circuit, they are going to bump into more nuclei. Okay, they can't actually bump into nuclei, but they're going to be deflected by the nuclei. So because of that factor, when temperature increases, the resistance of a circuit also increases. Okay, and you will find when you buy wires for use in household wiring, they will measure an optimal, they will come with an disclaimer about the optimal temperature on which it should be functioning. Okay, so all this goes to say that conductors do get heated up as a result of their resistance, and when they get heated up, it can result in some disastrous situations, and that heating effect of resistors is what we will have to look at next, but that we will do in the following class. So unless there are any other questions or doubts to be discussed, we can stop now.